So in this example, we want to find the values of k, or the positive integers k, for which the series is convergent. The first thing we're going to do, or what I like to do here, is ignore that I'm trying to find the positive integers k, and just try to determine if the series as is convergent or divergent. So if we're going to check to see if it's convergent or divergent, we want to apply a ratio test. So we're looking at the limit as n approaches infinity of a sub n plus 1 over a sub n. And remember that if that limit is less than 1, then the series will converge. If it's greater than 1, or if it doesn't exist, then it's going to diverge. And if it's equal to 1, then the test is inconclusive. So let me erase this right here for a second, and let's begin by finding what a sub n plus 1 is. So our a sub n plus 1 is equal to n plus 1 factorial to the second power over k times n plus 1 factorial. So a sub n you already have, so let's see where that takes us. We're going to have the limit as n is approaching infinity of n plus 1 factorial to the second power over, I'm going to put kn plus k factorial. So all that I did there is I distributed the k, and then we are going to take the factorial. And then we're going to say times, we have divided by a fraction, but that division is multiplication of the reciprocal. So I'm going to put kn factorial over n factorial to the second power. Now, go a little bit slower here. We have the limit as n approaches infinity of n plus 1 factorial. Let me write that down on the side. So n plus 1 factorial to the second power. Okay. So n plus 1 factorial is really equal to n plus 1 times n factorial. And if we want to square both sides, then this is equal to n plus 1 squared times n factorial to the second power. Okay, so let me write that down. N plus 1 squared times n factorial to the second power times kn factorial over, okay, here's what we're going to be careful here. The n factorial to the second power, I'm going to keep n factorial squared. And then let's talk about kn plus k factorial. If you have 8 factorial, then this is really equal to, let's say, 8 times 7 times 6 times 5 factorial. Or if we have 100 factorial, you really have 100 times 99 times 98 times 97 factorial. And you want to go as far back as you want. If you have, let's say, 17 factorial, you can also say that this is 17 times 16 times 15 factorial. And again, you can go as far back as you want. So this 7 is really 8 minus 1. The 6 is 8 minus 2. The 5 is 8 minus 3. So you have 8 times 8 minus 1, 8 minus 2, 8 minus 3 factorial. So the 100 really is 100. The 99 is 100 minus 1. The 98 is 100 minus 2. And then you get the idea. 100 minus 3, and then the factorial. So if you have x factorial, then that is equal to x times x minus 1 times x minus 2 factorial. You want to go as far back as you want. So if we have, this is why I'm doing all this, if we have kn plus k, I'll do it over here because I'm going to need space, kn plus k factorial, then this is going to be kn plus k times kn plus k minus 1 times kn plus k minus 2 times kn plus k minus 3. I'll do one more. Times kn plus k minus 4 factorial. And you want to go back as far as you want. You can go all the way back to, I'm going to write a few of them. You can go back to, let's say, kn plus k n plus k minus 1, and then minus 2, minus 3, minus 4, all the way to, let's say, kn plus k minus k factorial. So the denominator, we can break it up into, in this is what I mean by the denominator. We can break it up into kn plus k, kn plus k minus 1. And you're going to do this all the way to, let me just write one more. Kn plus k minus 2. And then you're doing this all the way to kn factorial. We can simplify a couple of factors. We have the limit as n is approaching infinity of, let's simplify a couple of things. We can simplify n factorial square with n factorial square. What else can we simplify? We can simplify kn factorial with kn factorial. And we're going to be left with n plus 1 to the second power over, so n plus 1 to the second power over kn plus k, kn plus k minus 1. And then we're going to have kn plus k minus 2. And then the idea here is that you're going to continue. You're going to continue up until this right here. Okay? Well, it's not going to matter much, and I'll tell you why. If you start multiplying all of the first terms, you are going to have the limit as n is approaching infinity of the numerator. You're going to have n squared plus something, 2n plus 1. But the denominator will have kn to some power. So let's say we're going to have kn to the power k, and then plus a couple of other terms. Do you agree? Well, you can clearly see that the degree of the denominator, is greater than the degree of the numerator. So it doesn't matter what k is, that limit will always be equal to 0 if k is greater than or equal to 2. Let's find what that really is. So let me Let me go back. So remember, the original problem says for what or for which positive integers, right? So positive integers. Why don't we let k be equal to 1? If you let k be equal to 1, I'm just looking at the first terms here. We're going to have the limit as n approaches infinity of n squared plus something over n, because we have k equal to 1. So you have 1 times n over 1 plus something something. So when your k is equal to 1, the first terms in the numerator and denominator are n squared and n. And that limit is going to go towards infinity. Therefore, if k is equal to 1, the series will diverge. Let me come back to it. So we have n factorial over k is 1, so kn factorial is divergent. And you can plug it in. If your k is 1, then you have the sum of 1 as n goes from 1 to infinity, and that sum will be infinity, or it's going to diverge. Now, what happens if k is equal to 2? If k is equal to 2, the first terms, we have the limit as n approaches infinity of the denominator of k is 2. You're going to have 2n to the second power plus a couple of other terms. This is n squared. But the first terms are that, and this gives you the limit as n is approaching infinity of n squared over 4n squared. Remember, we're adding a couple of other terms after. And that limit is going to be 1/4, and 1/4 is less than 1. Therefore, the series will diverge. Will converge. I was looking up here to copy the problem, and the divergent word came out. Okay, so if it's equal to 2, then it's going to converge. And then if it's greater than 2, let's say you have the limit as n is approaching infinity. And then you're going to have n squared over some number and then n to the third power or to the fourth power. Because remember, we're talking about k n to the k power. So if k is, let's say, 3, some number greater than 2, if it's 3, then you're going to have, I'll put it down as 27 plus a couple of other terms, and that limit is equal to 0. 0 is less than 1, therefore convergent. You can plug in 4, you can plug in 5, you can plug in whatever number you want. So for k values greater than 2, your series is convergent. So we can say that the series as n goes from 0 to infinity of n factorial over kn factorial is convergent for k values that are greater than or equal to 2. If you want, you can even go back here. Let's go over here. And you see I left the dot, because then you're going to go back to, kn plus k, kn plus k minus 1, kn plus k minus 2. And then you're going to continue going back, let me put the pink color, all the way to Kn plus, remember, where did we have it? So remember we have Kn plus K minus K. So right before this, we are going to have Kn plus K. Not plus K. So we're going to have Kn plus K minus K plus 1. The previous term is that. And when you simplify, then that just gives you Kn plus 1. And the idea here is that you're going this way. So if you're going this way, is plus 1. When you're going this way, is plus 1, you see? 97 plus 1 is 98, 99, and 100. So this last term that you have is going to be the Kn plus 1 term. So what you want to do, if you decide to FOIL the numerator, you have n squared plus 2n plus 1. But then in the denominator, when you multiply all of those binomials, it's too long of a problem to do, which is why I only left my first terms. All right, here we have another long example. So I'm going to stop here, but in this problem, we were looking for the values of k such that the series will converge or diverge. Okay. So if I go back to the original problem, if I let if I let k be equal to 1, then the series will diverge. But if I let k be equal to 2, then it'll converge. Or if I let it be 12, then it'll converge. If I let it be equal to 122, it will converge. Why? Because I just found all the values of k for which this series is convergent.